Machine learning (ML) solutions are transforming industries by enabling data-driven decision-making. In the DP100 course, we delve into the intricacies of designing and preparing ML solutions. This journey begins with understanding the core concepts of ML, the types of problems it can solve, and the potential it holds for various applications. From predicting customer behavior to automating complex tasks, ML solutions are at the forefront of technological innovation. The first step in designing an ML solution is to thoroughly understand the problem at hand. This involves identifying the business objectives, the type of data available, and the desired outcomes. For instance, if the goal is to predict customer churn, one must gather historical data on customer interactions, purchases, and feedback. Understanding the problem helps in selecting the right ML approach and setting realistic expectations. Data is the backbone of any ML solution. Collecting relevant data from various sources such as databases, APIs, and web scraping is crucial. Once collected, the data needs to be cleaned and pre-processed. This involves handling missing values, removing duplicates, and normalizing data. For example, if you're working with customer data, you might need to standardize the format of phone numbers and addresses. Proper data preparation ensures that the ML model receives high-quality input. Feature engineering is the process of selecting and transforming variables to improve the performance of an ML model. This step involves creating new features from existing data, such as calculating the average purchase value or the frequency of customer visits. Effective feature engineering can significantly enhance the predictive power of the model. For instance, in a fraud detection system, features like transaction amount, time of transaction, and location can be crucial indicators. Selecting the appropriate ML model is a critical step. Different problems require different types of models, such as regression, classification, clustering, or reinforcement learning. For example, predicting house prices might require a regression model, while identifying spam emails would need a classification model. Understanding the strengths and limitations of various models helps in making an informed choice. Additionally, considering factors like model interpretability and computational efficiency is essential. Once the model is selected, it needs to be trained using the prepared data. This involves splitting the data into training and testing sets, and then feeding the training data into the model. The model learns patterns and relationships within the data. After training, the model's performance is evaluated using the testing set. Metrics such as accuracy, precision, recall, and F1 score are used to assess the model's effectiveness. For instance, in a classification problem, a high F1 score indicates a good balance between precision and recall. Hyperparameters are settings that influence the training process of an ML model. Tuning these hyperparameters can significantly improve model performance. Techniques like grid search, random search, and Bayesian optimization are commonly used for hyperparameter tuning. For example, in a decision tree model, hyperparameters like maximum depth and minimum sample split can be adjusted to prevent overfitting and improve accuracy. Proper tuning ensures that the model generalizes well to new data. Deploying an ML model involves integrating it into a production environment where it can make real-time predictions. This step requires setting up infrastructure, such as servers and databases, and ensuring that the model can handle incoming data efficiently. For instance, a recommendation system for an e-commerce site needs to process user data and generate recommendations quickly. Monitoring the deployed model's performance and updating it as needed is also crucial to maintain its effectiveness. After deployment, continuous monitoring of the ML model is essential to ensure its performance remains optimal. This involves tracking metrics like prediction accuracy, response time, and system load. Additionally, the model may need periodic retraining with new data to adapt to changing patterns. For example, a model predicting stock prices would require frequent updates to incorporate the latest market trends. Regular maintenance helps in identifying and addressing issues promptly, ensuring the model's longevity. Designing ML solutions also involves addressing ethical considerations. Ensuring data privacy, avoiding bias, and maintaining transparency are critical aspects. For instance, in a hiring algorithm, it's important to ensure that the model does not favor candidates based on gender or ethnicity. Implementing fairness metrics and conducting bias audits can help in identifying and mitigating ethical issues. Ethical considerations are essential to build trust and ensure the responsible use of ML technology. To illustrate the process, let's consider a case study on predictive maintenance in manufacturing. The goal is to predict equipment failures before they occur, reducing downtime and maintenance costs. Data is collected from sensors monitoring equipment performance. Feature engineering involves creating variables like temperature fluctuations and vibration levels. A classification model is chosen to predict failure events. After training and hyperparameter tuning, the model is deployed to provide real-time alerts. Continuous monitoring ensures the model adapts to new data, maintaining its accuracy. Designing an ML solution is a multifaceted process that requires a deep understanding of the problem, meticulous data preparation, and careful model selection and tuning. As technology evolves, new techniques and tools will emerge, further enhancing the capabilities of ML solutions. Staying updated with the latest advancements and continuously refining the approach is key to success. The DP100 course equips learners with the knowledge and skills needed to navigate this dynamic field and create impactful ML solutions.